the trick here is you want to get an accurate loop iteration count. This is going to help you understand how these things work anyways, okay? And you also need to have an accurate pipeline diagram, all right? And the truth is, you really need to understand the pipeline hardware. I mean, you're writing this, fetch, decode, execute, memory, write back. But remember what the hardware looks like, right? I mean, it's more than just a slew of letters. Then you have to remember when the program counter has a valid branch target address. When does the program counter have a valid branch target address? If it's early branch completion, when is the PC valid? When the branch is in the execute stage. If it's the first one that we looked at, when is the PC valid? When the branch enters write back. So you need to know, when the program counter has a valid branch target address. You also need to know when the branch condition is known.
Now that the branch has been, now that the condition and the comparator has been moved in a new diagram.
Yes.
Is it a fetch decode mechanism now, or is it still
it's
an
the same
execute?
as it was. Fetch, decode, execute, memory, write back.
So it's still considered to be in the execution stage?
Yes. Well, no, it wasn't. It was never in the execution stage. In the old pipeline, we didn't know what the valid PC was until it entered write back.
Right.
And that was the source of that 3 clock cycle delay.
Okay.
And that's what precipitated us rearranging the hardware to get this early branch completion. All right? Then make sure that everything that is forwarded is drawn. In other words, is the data that you need really there yet? Okay? And then make sure that, depending on what kind of question I ask, what's the policy? Is it a flush policy? Is it a predict not taken policy? Does it use a branch delay slot? And then watch out for hazards that cause stalls. Okay? Sometimes, especially if you're using a spreadsheet, you start going fetch, decode, execute, memory, write back, fetch, decode, and you get in this autopilot mode where you're just going to go fetch and you miss something. So when you're doing these kinds of diagrams, these fetch, decode, execute, memory, write back diagrams, trying to figure out how long it takes for a piece of code to execute, similar to the quiz today, right? You have to be careful about looking out for things like hazards and how the loop iteration count. Mickey?
Yeah, loop doesn't mean that the branch. Dr. Moore.
All right, go ahead. So, here's the equation. Let me just tell you this. All right? The total number of clock cycles, how long this code takes, the total number of clock cycles is, here's the way you calculate it. It's the clock cycles before the loop. You see that? Then it's the number of loop iterations minus 1 times the clock cycles that it takes when the branch is taken. All right, you'll see that they can be different. So when this loop executes, it's going to execute one of 2 ways. It's either going to go down and come back up, or it's going to go down and fall through.
What's our loop mean again?
That's the iteration, the number of iterations of the loop.
Number of times the loop went through?
How many times does the loop body get executed? In a typical loop, suppose I tell you that the loop body executes 5 times.
So it's 5 times?
So I loop would be 5. It's
minus 1.
It's going to be 4 times when it loops back, and 1 time when it falls through.
Right,
Does that
okay.
make sense?
Yes.
And so that's what this calculation says. The total clock cycles is the clock cycles before the loop, then I loop minus 1 times the clock cycles when the loop branches, then plus the clock cycles of the loop body when it doesn't branch, okay, and then the clock cycles after the loop. All right? Clock cycles after the loop. All right? So we'll go through this exercise, and I'll show you that we get these numbers. All right? Show you that we get these numbers. All right?
cold up in here about before.
It feels good.
Okay. All right, so, let's see. I wish I could get rid of that. I can't. All right, so, good. Now remember, I hope this is visible to everyone. So here's the analysis. So here we go. I go in my initialization code, and I'm showing the forwardings. All right. Now here I get down. So what is this part right here?
That's the cycles that before the
That's
loop.
the clock cycles before. Do you see?
Yes.
Look, I stopped at 5. Look, 5, and when did I start? 1.
1
Look, I stopped at 5, I started at 1. So 5 minus 1
is 4.
is 4 cycles. So the clock cycles in the code that was before the loop was 4. So CC before is 4. All right? Now we're going to figure out how many clock cycles in the loop body when it branches. So here's a typical example of when it branches. Watch. Okay? Here's where it starts, right?
Mhm.
It starts on the fetch of the daddy. All right? Now, it presses on until it gets to here. Now, what policy are we taking?
It has to
Predict not taken.
Taken, okay.
All right? So, if we've used a predict not taken, then here we fetch the store double. But guess what?
We did it wrong.
That was wrong. So therefore, bam, we refetch at loop. Do you see it?
Mhm.
So now, when it branched, see, we stopped at 9.
Mhm.
You see it?
Mhm.
And we started at 5. So 9 minus 5 is
4.
4 cycles. So when the loop branches, the body of the loop takes 4 clock cycles. All right? The body of the loop takes 4 clock cycles. All right? Now, let's jump down to the case when the loop finally ends and see how long it takes. So here's the example of when the loop doesn't take.
Can you email me this?
No.
Why not?
Because this is one of the homeworks.
Oh.
Okay. This was the homework that everybody turned in and said, I don't know how to do this. This is
That's the last homework.
That was the last homework.
We
All right?
tried.
So watch. Let's try it now. So here we go. So I'm just going to start. I'm going to start it. It doesn't matter. It's not really at 1 and 4, but it doesn't matter. It's. Let's see how long it takes. So here I start. I do the at loop. I do the fetch. Blah, blah, blah. Here's the BNE. I do the fetch. Now what's the prediction?
Not taken.
Not taken, so it does the fetch. There we go. So this is clock cycle, well, it's not really 4, but relatively speaking, it's 4 minus 1 is 3. So when the branch isn't taken, how many clock cycles does the loop take? 3. Now, how long does it take for the code to finish? Okay, it takes from here till the halt completes, right? And when does the halt complete? In this clock cycle here, which is 10 minus 4 is 6. You see it?
Yes.
All right, so now, with all that information, if we go look at this code again, there we go. Clock cycle before we decided was 4 cycles. The clock cycles when it branches are 3. Okay, the clock 4 rather. The clock cycles when it doesn't branch is 3, and the clock cycles after are 6. So therefore, what's the answer? How long should this thing take? Let's see, it should take, well,
17.
4 plus, now how many times does the loop execute?
5.
Well, let's be careful.
It actually goes. How many times does the loop execute?
Yeah, how many times does the loop execute?
What by your
Let's
the
find
total?
out. here's I.
Okay, hold on.
Presumably,
You
let's
finna
find
go,
out.
you finna do it, do it.
So we load into R1 I, right?
Right.
Now, okay, what happens here?
It double,
We decremented it, right? So now what's R1 containing?
4.
4, right? Now, so, here we go, ready? What happens here?
We,
3, 2, 1, 0. So how many times does the loop execute?
cause it decremented each time once.
Yes. Try it again. What's I start with? 5, right? What happens here?
5 minus 4.
So now it's got 4, and that's not in the loop yet, is it?
Mm-mm.
Now what does I have? What does R1 have? Here.
4.
No, it had 4. It had 4 here. Now what does it have?
3.
It's got 3. There's once through the loop.
Right.
Okay. All right. Is that 0?
No.
Okay. 2. Is that 0?
No.
1.
yeah.
Is that 0?
No. It's 0.
Is that 0?
Yes.
So how many times did the loop execute?
4.
4 times. All right, so let's see. So 4 plus 3 times 4 is,
3 times 4?
well, isn't that what it says? I loop, which is 4, right?
Right.
4 minus 1,
That's 20.
4 minus 1 is
3.
3.
3 times
Okay, I get you.
4 is 12.
12.
Plus 4.
Plus 4
4.
is,
16.
plus 3 is,
19.
plus 6 is
25.
25
That is not
points.
the question I got to ask you.
But how come that's not the right answer then down there?
It is.
Cause 4 plus 4 is 8.
That's 7.
It's not
It's
4 plus-
17.
No, try it again. What's I loop?
Okay, I see what you did.
I said 5 times, and you said 4 times.
Four.
Now listen to this. This is what I'm saying. On the quiz, you counted that 1. You see what I'm saying? But then on this, you didn't count that 1 before it hit the loop. Before it hit the brain.
They're 2 different pieces of code, first of all. Okay, but more importantly, the question was, how many times does, when I say to you, how many times does a loop execute?
I'm talking about the whole thing, right?
That's analogous to saying, how many times is this instruction executed?
Right.
That's the equivalent statement. How many times do I find myself?
That's why when you put it on the quiz, this loop executes 2
2 times. That means I found myself at loop twice. I found myself at the place called loop twice.
Not the whole.
All right, good. So then, now, let's move on. All right, here we go. So, remember, I loop is 5 minus 1, which is 4. So this guy executes 4 times, right? There was the analytical solution that we did there. All right, well, guess what? You can do it in WinMIPS, early branch completion, predict not taken, and then other features. All right? All right? There we go. Now, why is it? Okay, good. So now what did we get before? We got 25. So why am I showing, what did I do wrong? Or am I showing the right code? Hold it. Is this the same piece of code?
No, sir.
Is it a different piece of
It's
code?
a different piece of code. Cause you can tell by the last store. The last store on what we just did was store R3X, and that one is store R1 something. I can't read that small right now.
So here we go. All right, so anyway, good. Thanks. Yeah, if the architectures don't match, you might have to play some games. All right? So there are some when you're using WinMIPS, if you get a pass 1 error, and probably everyone's seen this already.
Yes.
Okay, that means you got a syntax error in your code. You can get a pass 2 error, and it'll highlight where your error is. All right? Right now, in the configure menu, probably the only thing you're going to need is to either enable or disable forwarding. Quite frankly, everything we're going to do in this course is going to be forwarding enabled. Okay? It turns out that you can double-click an instruction in the code window, and that'll cause it to have a breakpoint.
Really?
So it'll run until it hits that instruction. bam, and it'll stop.